We were discussing the second method to determine the quantity of air required for stoichiometric combustion of fuel. And we said that to use this method, we need to determine what is the percentage of carbon. Okay, what is the percentage of carbon in, 1 second, sorry. Okay, we need to determine the percentage in carbon in our mixture and the percentage of hydrogen, and both are percentages in mass. So to determine these percentages, we should go back to the given. In the given, they said that our fuel is constituted by 80% in mass of C3H8 and 20% in mass of C2H6. So if we have 1 kilogram of fuel, this 1 kilogram of fuel will contain 0.8 kilogram of C3H8 and 0.2 kilogram of C2H6. Now, in order to know the mass of carbon in this 0.8 kilogram of C3H8, what should we do? We should find the percentage in mass of carbon in C3H8. Yani we can say that C3H8 will contain carbon and hydrogen, okay? But to determine the mass of carbon contained, we should do 0.8 times the percentage in mass, okay? The percentage in mass of carbon in C3H8. Because the percentage in mass, if you want, will represent the mass of carbon in 1 kilogram of C3H8. And since we have 0.8 kilogram of C3H8, we just have to multiply by 0.8. Okay, now to get the percentage of mass of C in C3H8, it's very simple. It's the mass of C present over M C3H8. Okay, now what is, if I consider to be able to find this ratio, all I have to do is to consider one molecule. If I have one molecule of C3H8, because you know, whatever is the quantity, the percentage is the same, okay? If I have one molecule of C3H8, what will be the mass of carbon in this molecule? It will be 3 times, if I consider a kilomole, okay? It will be 3 times 12. While the total mass of this kilomole of C3H8 is 3 times 12, which is the mass of carbon, plus 8 times 1, which is the mass of hydrogen in this kilomole of C3H8. So in this way, okay, by doing 0.8 times this percentage, I will find what is this represent. So when I do times 0.8, it will represent the mass of carbon that is present in this 0.8 kilogram of C3H8. But the source of carbon is not only from C3H8, but we also have carbon from C2H6. So we should add to this the mass contained in C2H6, which can be calculated as 0.2, which is the percentage in mass of C2H6 in 1 kilogram of fuel, times the percentage now of carbon in mass in C2H6. So to get it, we do the same method, but instead of considering a kilomole of C3H8, we consider 1 kilomole of C2H6 over the mass of 1 kilomole of C2H6. Okay, to do this, we say in 1 kilomole of C2H6, we have 2 kilomole of C. So the mass will be 2 times 12, which is the molar mass of carbon, over the molar mass of 1 kilomole of C2H6, which is 2 times 12 plus 6 times 1, so plus 6. So when you do this calculation, you will obtain the mass of carbon C. So this is equal to C. This is the mass of the percentage in mass of carbon that is present in 1 kilogram. Okay. So now this is for C. For H, you just have to say, since I just have C and H, if I obtain the percentage in mass of carbon in my fuel, H will be simply 1 minus C, because the summation is equal to 1. Okay. And now, once I got C and H, I just have to replace in the formula of the previous problem to determine the quantity of air required for stoichiometric combustion. Okay. Any question on this part? Okay. Now, second question is to calculate the change in volume during the combustion process. Okay. Whenever they ask me to find the change of in volume during the combustion process, this is equivalent to find the change in kilomole, because we know already that each kilomole of any gas, okay, will occupy the same volume. So 1 kilomole correspond to 22.4 meter cube. Okay, so in order to find the change in numbers, we can say that delta V is equal to 22.4 times delta N, which is the change in number of kilomole. Okay, and to find actually what is delta N, the change in number of kilomoles, all we have to do is to go back to our chemical reactions. In case you use the first method, in the first method we considered that if we do the analysis per kilogram, and here they should specify for you, okay, if to do the analysis per kilogram or per kilomole, it should be clear. Let us consider they asked for 1 kilogram of fuel. So we should start from the chemical reaction, which is A C3H8 plus B kilomoles of C2H6 plus, if you remember, we calculated together, okay, we calculated the number big N for C and D coefficient, but it's similar. يعني هلا we'll derive it together again. We can call it X if you want. We can calculate the number of kilomole X of O2 required. That will give me CO2 and H2O. For CO2, we said that the coefficient will be 3A plus 2B times CO2. And for H2O, it will be 8A over 2, so 4A, plus 6B over 2, so plus 3B, H2O. Now, to determine the value of X, we said that X, to calculate X, we can say that 2X, which is the number of kilomole of O, Okay. If you want, you can do the analysis for O2, and you can say X kilomole of O2 will correspond to, for CO2, you have 3A plus 2B kilomole of O2. And for H2O, you need to divide 4A plus 3B by 2, because each 2 kilomole of O will form 1 kilomole of O2. So you can add plus 4A plus 3B over 2, which is 2A plus 1.5B. Okay, so we end up that big X is equal to 5A plus 3.5B. So now if we want to find the change in number of kilomoles, delta N, so delta N is the summation of number of kilomole in products minus summation of number of kilomoles in reactives. So if we do the difference, okay, we have the following. We have 3A plus 2B, so delta N is equal to 3A plus 2B plus 4A plus 3B minus, so now we sum the number of kilomoles in reactives, so minus A plus B plus X. Okay, so let us replace X by its value. We have already 3A plus 4A, 7A, minus A, so 6A, and minus 5A, so in total it's A. Now for B, we have 2B plus 3B, 5B, minus B, 4B, and we have 4 minus 3.5, so plus 0.5B. We can deduce then that since the number of kilomole of product is larger than the number of kilomole of reactives, that the volume during the combustion process will increase. And to calculate delta V, we just have to multiply this by 22.4. Okay. Now, calculate the heat of combustion of the mixture, knowing that the heat of combustion of C3H8 is 50.35 megajoule per kilogram, and the heat of combustion of C2H6 is 51.9 megajoule per kilogram. So here, since the analysis is per kilogram, okay, you need to use percentages in mass. But if the given was in megajoule per kilomole, then you should convert your percentages from percentages per mass to percentage per volume. Okay? Because when you say I have the heat released per kilogram, you should multiply by the mass of C3H8 present in the fuel. Okay? To get what is the heat released from the combustion of C3H8. And you add to it the heat that is released from combustion of C2H6, which is the mass of C2H6 present in this fuel, times the heat, okay? So heat released. So you need to consider, in this case, percentages in mass, because the unit is megajoule per kilogram. But in case, I repeat, it was megajoule per kilomole, pay attention to convert your percentages from percentage in mass to percentage in volume. So you can say that the heat of combustion, you need to determine the heat of combustion Q. So what is Q in megajoule? That will be released if we have combustion of 1 kilogram of fuel. Okay, so to be able to answer, you say, I know that 1 kilogram of fuel is decomposed into 0.8 kilogram of C3H8 and 0.2 kilogram of C2H6. And since I know that 1 kilogram of C3H8 will release 50.35 megajoule per kilogram. So to know the quantity released by 0.8 kilogram, I just multiply by 50.35 megajoule per kilogram of C3H8, okay? So per kilogram of C3H8. I should add to this the energy released, so plus the energy released from 0.2 kilogram of C2H6. So to get this energy, I multiply it by the energy released by 1 kilogram, which is 1.9 megajoule per kilogram of C2H6. Okay, so always keep in mind that whenever I have any variable per unit mass, I multiply by the percentage in mass. If they have the variable given per unit volume, I should multiply by percentage in volume. And we have seen in this session how to convert from percentages in mass to percentages in volume. So now we can determine then for this mixture what will be the heat of combustion. Okay. Any question on this? Now, for question, if you want, for question 2, in order to calculate the change in volume during the combustion, I said we have two approaches. The first approach was to consider the whole reaction, okay? But also if you did the analysis using C and H, and if you didn't combine all reactives in one equation, you can also do analysis. And you can say that if I did the analysis for 1 kilogram, okay, of fuel, we said that in this kilogram of fuel we have C kilogram of carbon, okay, and H kilogram of hydrogen, and this correspond to as we said, we can determine from here the number of kilomole of carbons that we have and the number of kilomole of hydrogens that we have, and we deduced together that the number of kilomole of O2 required will be C over 12 plus H over 4. So this is the number of kilomole of O2 required. Okay. Now, in our reactives, what are our reactives here? So we decomposed the equation into two parts. We said that in our reactives, we have 80% of mass of C3H8. And we said that we can determine in this 1 kilogram, what is the number of kilomole of C3H8? We named it A. Okay. And what is the number of kilomole of C2H6? We named it B. Okay. So we said that in this case, if we want to find the variation in number of kilomoles, we have to determine for 1 kilogram, what is the number of kilomoles that we have. So in total, the number of kilomoles that will be present in 1 kilogram of our fuel is just the number of kilomole A of C3H8 plus the number of kilomoles of C2H6. So just we have to do A plus B, and we add to it the number of kilomole of O2 required, which is C over 12 plus H over 4. Now, concerning the products, we said that for the products, we have CO2 and H2O, okay? So for CO2, we know that the number of kilomoles of CO2 that is formed can be found from the chemical reactions. Okay, so we have two chemical reactions. We can determine the number of kilomoles of CO2 in products and the number of kilomoles of H2O in products, and then we do the difference. So you'll obtain exactly, if you do the two methods, you'll obtain exactly the same result. Okay, you can try the two methods and make sure that the two methods will give you same values for delta. Okay, so this is about how to calculate percentages in mass and volume, how to find the stoichiometric quantities of air, how to find change in volume during combustion, how to find heat of combustion, etc. All of these information are important in order to, if you want, assess the heat released, assess the quantity of CO2 emitted, and try to limit as much as possible this quantity. And if we cannot limit it, we need to go to techniques that can reduce the harmful effect of CO2. We already discussed possibility of capture and storage of CO2. Okay. Any question on these problems? Okay. I will introduce also a new concept which is related to internal combustion engines. So one of the main applications of fossil fuels is to use it in internal combustion engines. And in this case, we have, if you want, production of work from the heat released by combustion. We have seen already one application of fossil fuels to be used in power plants. The idea was to have a thermodynamic cycles. The heat will be used at evaporator as input, and we have a turbine that will lead to generation of output. It can be here electrical generation. Now, another application for fossil fuels is to use it in internal combustion engines. And in this case, also, we will transform heat into work. But this work is not electrical, it's a mechanical work. This mechanical work will lead to, if you want, rotation of the crankshaft. And with a transmission systems, we can deliver energy to wheels to drive the car. Okay? And we have several types of cycles for internal combustion engines. We'll discuss one of them in this problem. So they are saying that an internal combustion engine is characterized by an admission of air at a pressure of 0.1 megapascal and a temperature of 303 Kelvin for a volume of 0.3 liters. Volume expansion ratio during the combustion is 1.6, and during the compression, the ratio is 30. Assume that the combustion process takes place at constant pressure, the heat rejection takes place at constant volume, and the compression and expansion are isentropic processes described by PVK equal to a constant. And consider ideal gas behavior with K equals to 1.4. We want to try together first to draw this combustion cycle and do the analysis of what is happening in our engine. Okay, the idea is as follows. So we need to draw P function of V, and at the same time we'll explain the physics of what is happening here. You know that in majority of our cars, okay, we rely on piston cylinder systems to transform the energy released by combustion to mechanical work. And the idea is really simple. If we consider a piston cylinder system, you have here, let's say, the mixture of air plus fuel, okay? So air plus fuel. And this mixture will undergo a cycle, okay, of mainly 4 phases that we'll discuss together. And the piston will be related by a rod to the crankshaft. To be able to transform the energy of combustion into work, this work first will lead to translation of the piston, and the translation of piston will be transformed to rotation of the crankshaft. So this is in summary what is happening in internal combustion engine systems. And in this way, we convert heat into a useful work. Okay. Now, we need to understand what will happen inside the cylinder. So first, they told us that we have the initial characteristics given. So if we consider this is point 1, at point 1, we know the pressure, 0.1 megapascal. We know the temperature, T1 equals to 303 Kelvin. Okay, and we have the volume at this point is also given. So we can transform it to meter cube. So it's 0.3 times 10 to the power minus 3 meter cube. So in general, we work for pressures with Pascal. Yani we multiply here by 10 to the power 6 to get the pressure in Pascal. And we multiply the volume by 10 minus 3 to get the volume in meter cube. So 0.3 times 10 minus 3 meter cube. Okay. Now, we want to draw the cycle of what is happening in the cylinder. First, we have initial condition before, if you want, just at admission. Okay. Now, once we have, if you want, the charge that is entering at conditions given at state 1, we want to compress it. We compress the charge. And they said that the compression process is isentropic, and they gave us the equation of this process. So from 1 to 2, we have isentropic process. If you remember from thermodynamics chapter, we have seen that isentropic means adiabatic reversible. So no heat exchange during this phase. Q equal to 0 between 1 and 2. We just have work. Okay. After this, when we compress our fluid, it will reach high value of pressure and temperature, and then it will be ready, if you want, when we inject, and in case it's a diesel generator, we inject diesel. Once we start injection, after a certain time, we have auto-inflammation of our mixture, and we have combustion process. The way we introduce the fuel, in case you have a diesel system, depending on the law of injection you use, this will affect the combustion process. In this example, they said we will introduce diesel in a way to have a constant pressure process. So combustion, if you want, will release heat, and because the piston will start to move downward, the pressure will be able to remain constant. Since the volume is increasing and we have heat release, so the pressure will remain constant in this case. After this, after combustion is over, we have the expansion phase. And the expansion is the phase, one of the most important phases here, because it's during expansion that we can extract work, useful work. Okay, so from 3 to 4, we have extraction of work from expansion. So we have production of work, if you want here. Work is produced, W out. While during the compression, we need to provide work to move our piston upward. So here we have Wn. And during the combustion process, we have input of heat. Since we have here a constant pressure process, during combustion, at the same time, we have input of heat, but we have also production of work because you have the expansion started, okay? So you have here W out 1. So the work will be delivered into 2 parts. First, from 2 to 3, then from 3 to 4. So we have here a production of work. And finally, to be able to repeat the cycle, actually what will happen in the real scenario, we will exhaust gases. We will exhaust combustion gases. To simplify modeling approach, we're considering that it is equivalent to rejection of heat at constant volume. Okay, so here we have a heat rejection, and we told you in the given that the heat rejection is modeled as a process at constant volume. So here we have Q out. Okay, this is our cycle, and we need to do the analysis of this cycle. Okay, first, we said we should draw the combustion cycle. Second step, we need to find the properties at different points of the cycle. Okay, it's true that this problem is an application for chapter 4, but from your revision of chapters of thermodynamics, you will be able to do it. Okay, so you can consider that this problem is like a review for the exam, because it's a cycle and we need to do analysis of this cycle. Okay, we need to determine first at different points of the cycle what are the characteristics, so how to calculate pressure, temperature, and volume at these different points. Once we do this, we can evaluate the network, because you know by definition that the network of a cycle can be calculated by integral P dV. Okay, so all you have to do once you determine the volume at different points of your cycle, and you know the variation of pressure, so here you have constant pressure, here you have constant volume process. In constant volume process, no work is produced, so integral PdV will give you 0. For constant pressure process, the work output will be equal to P times delta V. While for the two processes of compression and expansion, since you have the formula PVK equal constant, you can perform the integration to find the work in and out. Okay, so here all we have to do in this step, we'll do this example together in detail next time, but today I will just give you the method and try to do it, because it is like a revision for the exam also, since we need to apply energy balances. We can use the concept of thermal efficiency, and here they asked for thermal efficiency. To calculate the thermal efficiency, we just have to determine we do the ratio of useful output over input. Okay, and once we do this, will ask us also to find the heat of combustion of the fuel used, knowing that the combustion efficiency is 90%. I just want to discuss this idea with you. So you know that the thermal efficiency of a cycle can be calculated as W net over the useful heat, okay? So over Q input. So now you have already calculated the network, and they asked you also to calculate the thermal efficiency, and also you can do it. So once you calculate this, you'll be able to determine what is your heat input, okay? And once you know your heat input, you can compare it with the heat of combustion. In ideal scenario, if we do the analysis of Q input in kilojoule per kilogram, if I don't have any losses during my combustion, okay, so I can consider that the input heat per kilogram of fuel should be equal to the heat of combustion in kilojoule per kilogram. But you know that you always have losses. So during combustion, sometimes not the whole mixture will burn, or you have some residuals, okay? That's why we define what we call the combustion efficiency. And the combustion efficiency can be assessed by considering the ratio of the input heat that I was able to extract in my cycle over the heat of combustion that is the theoretical maximum heat released, okay, during combustion. So if you want, from my cycle analysis, I will determine Qn. And I can determine it in once I get it in kilojoule, I divide by the mass, so I can get it in as a small q if you want, in kilojoule per kilogram. And once I get it, in order to determine the combustion efficiency, so here it's in the, if you want, they asked it in the other way. They gave me the efficiency, the combustion efficiency, and they asked for the heating value. Okay, so to get my heating, the heat of combustion in kilojoule per kilogram, all I have to do is to apply that the combustion efficiency is the ratio of the energy that I was able to extract from combustion, which represents the input to my cycle, over the maximum energy released, so which is due to complete combustion of my fuel, and which is given in kilojoule per kilogram. So in this problem, once you determine Qn from your cycle, and knowing the efficiency of combustion which is given, you can deduce the heat of combustion in kilojoule per kilogram. So please try to do this problem for next time, and we will correct it together in detail next time. Okay? Any question before we stop? Okay, thank you. Bye.
Thank you. Goodbye.
Bye.
Thank you.